Hi, my name is Yudai Tanaka. I'm a first-year PhD student at University of Chicago, Human-Computer Integration Lab. And as the first paper presenter at the whole conference, I will talk to you about DualVib. My co-authors are Arata Horie from University of Tokyo and Anthony Chen from UCLA. Let me first show you what DualVib is. DualVib is a handheld device that can render the haptic sensation of objects including movable mass, which we call dynamic mass, ranging from mixing a cocktail to holding a chainsaw. Here we introduce the motivation behind DualVib. There has been a variety of research in virtual reality field that attempts to recreate the haptic sensation for grasping objects. However, often these devices are limited to objects with simple structure property, such as a cube. Recently, researchers have investigated rendering the haptics of a more complex objects, which involves dynamic force feedback according to users' manipulation. For example, a liquid container. In this respect, haptic devices are on the trend of increasing their versatility for simulating more complex objects. However, from a different perspective, to simulate this dynamic force, these devices involve displacing of actual weights, which leads to heavier and bulkier devices, which then also increase users' discomfort and making it less appealing to the consumer market. Other researchers tackled this problem by engineering novel ways of utilizing vibrotactile actuators, achieving compact and rigid form factors. Here we can see a trend where haptic devices are going for simplicity. Our motivation is to design a haptic device that is both versatile and simple. DualVib has versatility to grasping in VR by simulating dynamic mass, while preserving simplicity of its form factor. The key to this feature is that the device only uses vibrotactile actuators, 2 voice coils, and 2 linear resonant motors, which allows DualVib to avoid any bulky mechanical structures. Thus, the device is extremely more compact and lightweight compared to off-the-shelf vibe controller and other devices involving dynamic mass. Let's dive a little bit deeper into DualVib. DualVib's haptic rendering methodology is rationalized by the observation of actual interaction with dynamic mass. Here's one canonical example of dynamic mass. When we shake a coin box, we feel kinesthetic force exerted from the coins rattling inside. At the same time, we also feel the surface vibrations due to the collision between the coins and the box. To simulate the total sensation of manipulating dynamic mass, DualVib independently renders this kinesthetic force and the surface vibrations, here we call texture. For rendering forces, it is known that by setting the frequency and pulse width ratio to a specific value, a pseudo-directional force sensation can be generated. This type of vibrations is called asymmetric vibrations. We adopted this principle to simulate the force feedback for dynamic mass. As for rendering texture, the vibrations propagated on objects can be preserved in the form of auditory signal, as it already contains the envelope and intensity of original vibrations. So as previously demonstrated by Minamizawa, it's possible to reproduce the haptic texture by simply outputting the acoustic signal to the vibration actuators. We sample the actual vibrations of real dynamic mass objects beforehand using a contact microphone. The sampled data is then reproduced by the linear resonant actuator embedded in DualVib. So now the question is how we control the 2 vibrations. On a macro level, the vibe tracker captures the motion of the DualVib device. It passes the motion to real-time physics simulation. The simulation calculates the acceleration of inner dynamic mass. Then based on the acceleration, DualVib controls each vibration stimulus. Let me a little bit detailedly explain how this control works on a real-time basis. As depicted by the blue line, the amplitude of asymmetric vibrations simply follows proportional to the acceleration. The direction of asymmetric vibrations also corresponds to the plus or minus of the acceleration. And for the texture, DualVib outputs a 100 millisecond sample of acoustic vibrations when the acceleration surpasses a certain threshold, depicted by these blue dots. We conducted a user study with 12 participants to evaluate whether DualVib can properly represent different dynamic mass objects. We prepared 3 different materials: water, yogurt, and marble chocolates. They are the representatives of fluids with no viscosity and fluids with viscosity and solid particles. Then each of these materials has 3 different levels of mass. So in total, the participants were asked to identify 9 different types of dynamic mass. To understand the comparison between DualVib and either pseudo-force or texture feedback alone, we conducted the above task with these 3 interface conditions with a counterbalance holder. These confusion matrices show the average accuracy of all participants for correctly identifying the target dynamic mass objects. Overall, the results suggest DualVib can more effectively present different dynamic masses compared with either pseudo-force or texture feedback alone. For further understanding, we reorganized the confusion matrices by separating the results from the mass level identification from those of the material identification. For the mass level identification, the participants' answers are equally accurate in pseudo-force and DualVib, which confirms that pseudo-force feedback is responsible for rendering the kinesthetic force from dynamic mass. For the material identification, the accuracies are in the same level when comparing texture only and DualVib, which confirms the texture feedback is responsible for rendering the material properties of dynamic masses. These results altogether suggest DualVib can properly distribute both pseudo-force and texture feedback without interfering each other. We also conducted a user study with 8 participants to evaluate whether DualVib enhances the haptic realism of manipulating dynamic mass in VR experiences. We created 5 example applications for this study: shaking coin boxes, pouring hot sauce, mixing a cocktail, cutting the tree with a chainsaw, and recording a bazooka. Here we compare DualVib with the texture-only setting, which can be regarded as a representative of a conventional vibrotactile controller. The plot shows the participants' ratings of haptic realism in 1 to 5 scale. As you can see here, DualVib has higher mean scores compared with texture only. According to Wilcoxon's signed rank tests, we got the statistical significances for coins, chainsaw, and bazooka. Overall, the results suggest DualVib enhances haptic realism of dynamic mass compared with the vibrotactile baseline. In conclusions, here we summarize today's takeaways from a technical perspective. DualVib simulates haptics of dynamic mass while preserving its simplicity. It simultaneously distributes pseudo-force and texture vibrations, and it enhances haptic realism in VR for several applications. But from a meta perspective, this work stands on the attempt to create ultimate haptic actuators that can render any haptic sensation with a minimal form factor. Ideally, one actuator could become an ultimate actuator in the future, but today the capability of a single actuator is very limited. So researchers have combined multiple stimuli to complementarily overcome the limitations of individual actuators, which is called multimodal haptic feedback. For instance, rendering hand-scale collision by combining solenoid and vibration, or simulating body-scale collision by combining solenoid and electrical muscle stimulation, or simulating haptic sensation of dynamic mass by combining virtual force and texture vibration. Thank you so much for listening. Please also refer to our paper for details of technical configurations and user studies.